Good morning, everyone. I'm Kwang Park, and today I will be presenting Smart ECU, a scalable on-vehicle deployment of drivetrain fault classification systems for commercial electric vehicles. This research was jointly conducted by UNEST, GIST, and Hyundai. All the first detection in a vehicle's motor is essential. Why? Because fault components can eventually compromise your safety and degrade the vehicle's efficiency and performance. With this motivation, our primary objective is to develop an algorithm that can estimate the unknown status of motor. Ultimately, our objective is to achieve PHM, prognostics and health management for predicting and managing the overall health of the vehicle. Algorithms designed for fault diagnosis require three key specifications. First, low latency for real-time performance. Second, customer vehicle data must not leave the vehicle for security. And the third is an accurate diagnostics algorithm. Combining these, we realize that on-vehicle AI deployment must be our goal. Previous studies also attempt AI-based motor fault diagnosis, but they often utilized simulated data. This led to discrepancies with real-world data, potentially degrading the performance of AI. Additionally, existing AI models, due to their size exceeding 400 megabytes, could not be deployed on ECUs smaller than 10 megabytes. The final challenge is data imbalance. Fault data is generally difficult to collect or nearly non-existent, leading to the data imbalance problem. Our work, Smart ECU, successfully solves these problems through key contributions. First, we gathered and used real-world data. Second, we achieved true on-vehicle deployment. And third, we proved its generalizability. I will now explain it in detail. First, to collect real-world data, we acquired both normal and faulty vehicles of 7 different models from 19 customers. Next, we disassembled the motors and attached vibration sensors to the motor component before reassembling them. After that, we test drove the sensor-equipped vehicles ourselves, collecting data across 6 real-world scenarios, from full acceleration to steady cruising and braking. Through this, we were able to acquire 13 gigabytes of high-frequency data at 25 kHz. In summary, we collected 7 different vehicle models from 19 customers, gathered data in 6 environments, and accumulated a total of 13 gigabytes of 25 kHz real-world vehicle big data. Next is on-vehicle deployment. Existing AI models were 400 megabytes in size, making it impossible to deploy them on ECUs or MCUs that are typically around 10 megabytes. To address this, we designed a classification model with a bottleneck structure. This model takes FFT transformed data as input, and due to its bottleneck structure, compresses the data into a lower dimensional form. This allows us to reduce the model size. Finally, a classifier distinguishes between normal and fault states. Although the existing model achieved a performance of 99%, it could not be deployed on the model due to out-of-memory issues. Our model ultimately achieved 97.5% accuracy, and thanks to its compact size of 3 MB and STM32Cube converter, we can deploy the AI to board. After deployment, we conducted a single vehicle model test using the data of the same car model as the training environment, which included both normal and fault data. The result was successful. We achieved a high accuracy of 97.5% and an undevised latency of 5.6 seconds, a result unattainable by previous models. We successfully demonstrated that AI can operate on a board in a single vehicle. So what's next? The final contribution is generalization to more vehicles. As mentioned earlier, fault data is rare, so we could only manage it to collect data from about a vehicle. As you can see on the screen, most vehicles lack fault data altogether. This means the classification model is impossible. So we thought a different strategy. What you can see on the screen is a classification model. It requires fault data. Strategy is autoencoder. An autoencoder simply reconstructs input data, thus requiring no fault data. In the training phase, our autoencoder only sees normal data and reconstructs it. This results in low reconstruction error for normal data. Conversely, since it has not seen fault data during training, the AI reconstructs it incorrectly, leading to a high reconstruction error. In short, a low reconstruction error indicates normal, while a high error indicates a fault. This is the actual architecture of the autoencoder we used. As you can see here, it consists of two main parts: an encoder that compresses the data, and a decoder that reconstructs it. The encoder uses several layers of 1D CNNs to distill the input data down to its most essential features. The decoder then attempts to rebuild the original signal using only the compressed information. Through the CNN module, we were able to extract local features. Additionally, we aim to extract global features not captured by CNNs by adding an MLP layer. This allows our model to effectively learn both local and global features. So, why did we specifically choose this hybrid CNN autoencoder, aka why local feature is important? We chose a hybrid CNN architecture to efficiently capture both local and global fault patterns, directly infusing domain knowledge into our model. Guided by mechanical engineering expertise, we use the CNN because it specializes in detecting local patterns like characteristic frequency and sidebands that are the telltale signs of drivetrain faults. Since our autoencoder only requires normal data, we had to select high-quality normal data. Therefore, we conducted training using Ionified vehicles, which provided sufficient data for model aligning and allowed for appropriate evaluation. The experimental setup as follows. Training is performed on a single vehicle model with same model. Next, we evaluated the model's performance through an intra-car assessment, testing it on the same vehicle model used for training. We also conducted an inter-car assessment to evaluate performance on other vehicle models with limited data. Qualitatively, when confirming our model's performance across all vehicle types, we found that it clearly separates normal and fault states, as shown in the left figure. This was also verifiable through TSNA visualization. Leveraging this performance, we set the threshold between normal and fault as the maximum normal reconstruction error and proceeded with quantitative evaluation. The quantitative evaluation shows that our model achieved high accuracy performance of at least 85.4% and up to 99.8% across the 6 speed conditions and both intra-car and inter-car scenarios. Furthermore, our model achieved a high recall of up to 99.8%, confirming that cases where a fault is misclassified as normal are rare. In conclusion, Smart ECU is a world-first achievement. We successfully deployed an AI system on an ECU using real-world customer fault data. We proved that with the right strategies, on-vehicle AI is no longer a future concept, but a practical reality today. Thank you.